let's take a look at this polysaccharide, which is denoted using those N and M kind of notations, meaning that that's just a fragment of the polysaccharide chain. And let's discuss about the structural features and the properties of that polysaccharide. Especially, let's focus on answering this question, whether this polysaccharide is reducing or non-reducing, and in general, let's kind of see what kind of ends does it have. And with that, we are going to also answer this question regarding how many unique products we are expecting from that polysaccharide if we perform extensive methylation of that polysaccharide, and then after methylation, we hydrolyze all glycosidic bond in the structure of this polysaccharide. So first of all, let's talk about sugars at the end, at the very end of that polysaccharide chain. And that allows us to actually determine about the properties of that sugar as a reducing agent. So this notation means that this is just a repeating unit, right? So it will end with some kind of sugar right here, and from that side it will also have one monosaccharide which is just connected with just one neighbor. And based on the structure here, we can actually draw that structure. So most likely the structure on the reducing end will be exactly the monosaccharide that we have right here. And if you analyze the structure, so all of them are D-glucose molecules, right? So D-glucose, this is also D-glucose, and here you go, this is D-glucose, and we have alpha 1, 4, 1, 2, 3, 4 glycosidic bond right here, and here we have alpha 1, 6 glycosidic bond. So based on that, we can deduce the structure of the reducing end, the sugar on the reducing end, which is going to be also that D-glucose fragment. And here, of course, we may have a mutarotation. So because you see here, this OH group is not involved in the formation of the glycosidic bond, this sugar will be reducing because that particular unit can undergo mutarotation and become, in some very tiny amount of that, acyclic with an aldehyde group, and therefore it will be able to reduce, for example, copper 2 plus into copper plus, or silver plus into metallic silver. So this is a reducing sugar because of the OH at the what we name reducing end of the polysaccharide. So this particular monosaccharide we say is at the reducing end. So all polysaccharides, regardless of whether they are branched or linear, they will have just one reducing end. But for branched polysaccharide, we expect to have multiple non-reducing ends, and that's actually a good demonstration of that. So you see here the main kind of branch, right? And at every, I don't know, here we see every other glucose, but maybe we have more unbranched units before the next branch. But anyhow, from a certain point, certain glucose monomer serves as a branch point. Let me use a different color. So this is our branch point right here, right? Because that particular monosaccharide is involved in the formation of more than 2 glycosidic bonds. So for a linear polymer, each sugar kind of holds hand with 2 of its neighbors, but for branched one, at the branch point, you see as if the third arm kind of holding onto another branch. But for both those branches, we expect to see the non-reducing end being another glucose fragment. Oh, wait a second. I drew it not in a good way. Let me erase and draw it the same way as I drew the previous structures. Sorry, I need to make sure that I have my alpha right here. So I need to draw it above, right here. Okay, so this is my non-reducing end. And as you can see, the monosaccharide fragment at the non-reducing end will not have a free anomeric carbon. That's why it's called non-reducing end. And there will be two, actually. I need to draw another one right here on the bottom. Again, I will continue that bond because over here, I need to draw another glucose unit. Right? Oh, you don't see the end of that. Okay, so those are two non-reducing ends. And of course, there are many because we just see the one of those branches stemming up from the branch point, but we have more than one branch point right here in this polysaccharide. That's why we will have multiple non-reducing ends, just one reducing end. And by the way, this is the structure that you can expect for amylopectin that is found in starch and in glycogen. So yeah, let me highlight here that is reducing because of that, right? But now let's answer how many unique products of methylation and hydrolysis we expect to see. And so this is our branched homopolysaccharide. So for that kind of polymer, we can actually envision, each of the polymers. Let me label my anomeric carbon like that. Each of the monosaccharides engage in the formation of two glycosidic bonds, unless we have the very end. And then at some points, we have a branch point, and we have another branch coming out like that. That's a schematic representation of that. Yeah, so we may have another one right here. But all those units have the same chemical structure. So as a result, the types of products depend on actually arrangements of those glycosidic bonds. And definitely the one at the branch point will give us a unique product because it will have three unmethylated OH groups due to three glycosidic bonds. So we have OH group at the anomeric carbon, OH group due to the alpha-1,6 glycosidic bond, and OH group at carbon number 4 due to alpha-1,4 glycosidic bonds. But for OH group at carbon number 3 and carbon number 2, those will be methylated. Now, another unique product is expected for the monosaccharide in the branch, not at the branch point and not at any of the ends. And this one will look like that. So because this sugar has just two glycosidic bonds, so we expect two unmethylated OH groups corresponding to the positions of those carbon atoms to which were connected, which were involved in the glycosidic bond. But everything else is methylated. Right? That is the second type of the products. And then we have two types of ends. So we have this one, which is our reducing end. And here we have the sugar that has only one unmethylated OH group, and that would correspond to carbon number 4, right? Because that's how that terminal sugar established a connection with the rest of the polysaccharide. But everything else will be methylated. That is our reducing end. And finally, for the non-reducing ends, and they will be the same because they are similar, right? Regardless of whether it's a main branch or kind of the branch that stems out of the branch point. So we are referring to those kind of monosaccharides. And then here, this is our anomeric carbon, right? So only the anomeric carbon will be not methylated. Everything else will be methylated. And it should be down. Yeah, so I was drawing beta, but in fact it is alpha, right? So I need to redraw those in here, even though we can place them actually on the wiggly lines right there, right? Because again, mutarotation will be possible after hydrolysis. And going back to this one, so that will feature all other hydroxyl groups methylated. So we expect to see 1, 2, 3, 4 unique products.